Namaskaram. Nenumi Madia Unanduku Chala Santoshanga Unanu. I'm very honored to be here. Thank you very much for the organization of the work, of this fantastic workshop. And so my name is Daniel RACOCEANU. Everybody here is calling me Daniel, so please do so. I'm professor at Sorbonne University in France, and I'm PI at the Paris Brain Institute, which is a very nice research institution, a sort of mixture between private and public, and with about 800 people, and 20-25 research teams in different areas of biology. So I would like to talk about our destiny somehow, from the research point of view, from the AI point of view, from the human point of view. And I will not present this too much, but you certainly saw this kind of silent movie presenting you what AI is able to do now, just starting from keywords. So the kind of quality scenes they are able to generate purely from AI, and purely simply by giving a sort of simple query made by a human, right? So the quality and the inspiration of the scenes they are creating, starting just from a simple keyword, it's really amazing. So this is Sora now. What is interesting is that Sora in Romanian means sister. So I suspect that there are some Romanians in the loop. Why I'm saying that? Because I'm born in Romania, as you understood. So here an example of queries they are having and the scenes created just after. So you can visualize that online. I will not spend too much time, but it's quite amazing to see how these kind of movies are close to realistic. And of course, this will improve more and more because what we are seeing here is computer graphics, in fact. And the industry of computer graphics is already very professional, right? So Pixar, all these industries are huge industries and technologies exist. Connecting this to a keyword, it's something which is somehow easy to do. Maybe the way of composing these elements to create realistic scenes, it's something which has not been done before. But you can see all of these scenes, as amazing as it could look, are artificial. Okay, so another important element in AI, I believe, for us, it's AlphaFold. It's reaching a second version. It's becoming better and better. And I believe in the future people could use this platform for drug discovery reasonably well, and with more and more refinement, I believe. So I was joking with some friends saying that maybe one day AI will receive the Nobel Prize for a new drug discovery, who knows? I'm teasing you, of course. And now if I'm going back to the roots, so you may have heard about Alan Turing, right? So who was a sort of founder of the computers. I will not say computer science, of the computers. He made a computer to beat a very unbreakable, reputable unbreakable machine built by Nazi, Enigma, yeah? So maybe you saw the movie, Imitation Game. So what is Imitation Game about? It's coming back to the test he was designing when he was asking himself what will be the limit between the human and the AI, artificial intelligence. And he was imagining a test in which one day we will probably need to make the difference between the human and AI through a sort of evaluator who will not see who is speaking with, a human left side or AI at the right side, and without any additional element except the discussion by itself, he will need to, or she will need to, make the difference between the real person and the AI. Okay, and you can see this in the movie. You see a screenshot of this imitation game movie, which was quite interesting for me. Even from the human point of view, it was a nice example of dedication. So, according to Turing, the AI was related to the ability to mimic human intelligence. It's very interesting because, again, with some other friends, and somebody else was citing that, I guess, Woody Allen was saying that artificial intelligence, it's the opposite of human stupidity. So again, I'm teasing you a bit. He was teasing us a bit, but it's interesting to think about that, right? So the Turing test is this one. They design it in this way. And if I'm looking just as an example to one of the state-of-the-art tools, which is the generative adversarial network, the principle of the work is similar. So this was interesting for me, that we see now tools which are, let's say, at the state-of-the-art in generative industry technology, which are working based on the same principle. So if you take a look at the structure of a gun, you have a discriminator, which is a detective, which is like an evaluator, in fact. And you will have the original data, and you have a generator, which is creating also fake images. And somehow the discriminator, the evaluator, will make the difference between the real data and the fake data until it's not able to make the difference anymore. This is a sign that the generator is good enough. And this is how the generator reach this kind of quality level of the images or videos they are producing by this kind of game. And it's exactly the principle of the imitation game designed by Alan Turing. So now, of course, these technologies, the GAN technology, it's going further, and you have this sort of synthetic typical setup in which you have some random noise, you generate faces, you have a real face or a set of real faces, and you will make the challenge the discriminator to make the difference between both until he's not able to make it. And in this case, he will give back feedback to the generator to say, okay, you are not good enough, please do better and better and better and better until nobody will make the difference anymore. So we are in the stage in which finally the stopping element will be the error. The stopping element could be our perception. When we are not perceiving anymore a difference, then that means that AI is starting to be interesting for us, bringing us something. So the question is, okay, so are these AI models intelligent? Because they don't possess genuine understanding of the world, consciousness, self-awareness, or emotions, still. And this is essential. So the goal of AI is not only to mimic human intelligence in our opinion, but it's to develop an AI which can augment human capabilities. This is the real goal of AI. We don't need to forget that, especially in biomedical areas in which there is a responsibility we have as doctors, biologists, scientists for the future. So we need to use AI to augment our capabilities to operate ethically, responsibly, and contribute positively to the society. So all these images have been generated, by the way, so I don't have any copyright problems with it, right? Because it was instantaneous. So I'm good. So just, again, to challenge you a bit, when we talk about human and AI, There are a lot of elements of vocabulary which are used. How to do that? So people are talking about human in the loop in the classical way. So this is what we are doing also with our students in one of the example I will give about whole slide image analysis. An extended of the mind, an extension of the mind, human-centered AI, human-AI collaboration, augmented intelligence. So then, of course, crazier things, cyborgs in which we merge organic and machine elements. You may say that this is like crazy, but I was discussing with an ophthalmologist, and they are really thinking to build in the future a synthetic eye for blind people, because they start knowing how to connect it to the optical nerve. So I was surprised. Me, working in AI, I was surprised about what the ophthalmologist was telling me, that it was exactly this idea of the cyborg. Human-machine co-evolution, then you have centaurs, like half human, half machine. Okay, so again, I'm challenging you, I'm teasing you a bit. This is the scope of such a workshop, also is to discuss about these issues. But at the end of the day, we need to have responsible AI. And this is not only a politically correct keyword, because I know we are in a political campaign now in India, so I'm being politically correct, right? But it has content too. It has real content, which is, for example, to be fair in the decision you have, in the suggestion you make, to be ethical, to respect the privacy of the data, of the personal data, especially in medical, it's obvious, right? To offer a traceability. Why did you suggest that? To be accountable, to be careful about security. So in Europe we have the GDPR, which is now maybe one of the most advanced, I will say, set of rules and laws dedicated to protection of private data. Sometimes it's even too much for us, because if you started to work on a research problem and you sign an agreement with your patient to use his data for the plan A, and working on the plan A, you have suddenly an idea to go for plan B, you need to start over again and sign a new agreement, which is not always so easy, right? Sometimes the patients are not with us anymore, unfortunately. So things are not easy to set up from the research point of view. But I mean, probably this is the price we need to pay. And then last but not least, we need to think about the carbon footprint, because people are adding layers and layers and layers for the deep learning, creating monsters to do things. And sometimes they don't ask the question, do I really need this kind of monster to do it? Did I optimize sufficiently my model for the task I need to do? And this is an interesting question we'll try to raise. And then, of course, one of the components of the responsible AI, it's explainability. And then again, you have different methods of explainability. Maybe one of the simplest I like very much is explaining by example, because it's a very nice for example, if you try to explain to your grandmother what you are doing in research, you need to instantiate. If you need to explain to your kids what you are doing in research, you need to instantiate, to give examples, simple examples. This is a way to explain. We can explain by creating a text explanation, like you saw. We can create a model simplification paradigm. We can be local, global. We can be visual also. And visual explanation is one of the most interesting, because image somehow it's much more powerful than thousands of words if it's well chosen and well translated, transformed. So an interesting viewpoint was also about our mind. When we talk about what we are doing for a given problem, a user will start working with a system, a model. He will probably have at the beginning a sort of initial mental model, like you can see here. So we are creating our own mental model about the problem we are trying to deal with. So this initial mental model is usually not complete, even if the guy we have in front of us is an experienced expert, or he used to work not only in his expertise field, but also with AI. He may still have a sort of initial model which is incomplete. He will probably lack of confidence, or have an inappropriate confidence, or being scared about AI, say, oh, these guys they want to pick my job in the future, right, for example. Instead of saying, no, let's see which kind of advantage I can trigger from that. And the idea is that from this kind of initial instruction, initial model, through some quality criteria, some satisfaction tests, we can go to explain what we are doing. He can go and try to understand, interpret what we are saying, and then we try to give him or her an appropriate trust to move forward, to have a comprehension tests, performance test. All these can be traced and explained and quantified somehow in order to reach a more advanced mental model and reach also improved performances. At the end of the day, of course, we will have an appropriate use of the model we are proposing. So this paradigm of the evaluation of a system and the evolution of the mental model of the user, it's very interesting to think about, I believe. And of course, then I was representing here the classical loop in blue, in which you have at the beginning training data set, annotation, classification, which is a classical way of working with AI. You have the AI doing the learning process. Then you will have to work just in inference mode here by presenting the new case, data, decision, annotation generated by, and then transfer that to the user. This was the classical loop. Now, if we try to bring explainable AI inside, we go with the red part. We need to have some explanation at the beginning in the models, or to present a way in which we explain, as I was telling you, text, model simplification, local, global, visual. Then you have this kind of explainable AI, XAI framework, which is created. And you will be able to provide a justification, an explanation to your user, to your expert, because he's the expert of the area normally. And then there is an important part, which is the comprehension. Did I understood exactly what you want to say, what the model wanted to say, to suggest me? Do I agree with that or not? And then have the possibility through an interface, especially in the learning phase, to give back this kind of perception in order for the experts to adapt their system, to add more knowledge, change the knowledge, to adapt it again, and start the loop again until we are reaching a good level of understanding in which we have a nice error curve and error evolution, right? So of course all this could be done through the classical way, creating loss functions, adapted loss function. Finally, the loss function, it's a tool for us to create what we want to create. Don't be afraid to create your own loss functions. You can take general or generic loss functions, but you can compose them as you wish. You can create even your own loss function, so don't be afraid about that. And of course, at the end of the day, when we are in autonomous mode, we will create a pipeline in which this kind of interaction will be shorter, because we have a model, we have all the paradigm of the explanation, and we generate the explanation to the user. We can still collect this kind of feedback in order from time to time to try to update, upgrade our system. So the idea is to enter in the new epoch, age, in which we should ask ourselves, why did you do that? Why not something else? When do you succeed? When do you fail? When can I trust you? How do I correct an error? These are the questions we need to ask more and more when we have such a model, right? So then we reach something which is very important for me, is the counterfactual reasoning. So I like this representation using an iceberg, because the factual is what we see, usually, what happens, and the counterfactual, it's all kind of possibilities we can think about, possible and impossible, and why. What if is the classical question for counterfactual. So if I have an AI system suggesting me that I couldn't have a loan, I don't like this idea. I would like to know what should I do in the future to be able to get the loan, right? So this is counterfactual explanation. We need to explain to our users how to use our system in order for them to be better, to become better, or to create a paradigm which is successful for them. And then when we talk about counterfactual reasoning, we have a different type of reasoning. Usually you are maybe used with deductive reasoning, in which we go from theory to the world, abductive reasoning, which is going from the world to the theory. Counterfactual is going from the theory to a sort of possible world. And it's going back and forth somehow. From the factual world, we go through abductions to actions and to predictions to a counterfactual world. So for me, this is something which is important. Now, talking about exploring the borders of the universe, of the world we know. XAI has an interesting role to play. So my opinion about that. So the world we know is modeled usually using classical mathematical models, equations, derivative, partial derivative equations, matricial equations. When we know, we can do that, and we like to do it. Why do AI? No need. No need. Nobody needs to bother if everything is clear, is known, right? This is the known world. There is an unknown world we are not sure about. Then, of course, we have the statistics to analyze the past, and we have the probabilities to envisage the future. Based on the statistics, we create probability theories to try to go and explore this new world, right? Probabilities, one of the major elements in this part of the story, is the Bayesian, which is conditional probability. Based on facts I know, or I suppose I know, I can try to imagine what will be the conditional probability for new facts, new events, right? Or new hypotheses. And finally, here I will need AI, because AI is that, is statistics, probabilities, a mixture of both, right? So this tool is done specifically to explore a new part of the world, which I cannot model with classical systems. And then this is the kind of paradigm in which, okay, I'm exploring the new world with XAI, with AI, but then I need to understand what I'm doing. And this is where explanation is coming in, because I need step by step to explain what I'm doing, to understand what I'm doing, in order to go as fast as possible to classical models, in which I have everything inside. Everything is almost deterministic, no surprise. I can program that, I can use it fast, everything is clear. So once I know something, I will try to use classical models, traceable models. No probabilities, no statistics. But AI is very good to explore a new domain, to try to understand this new part of the world. And this is the kind of paradigm we were trying to set up in our research. And for example, in Esther research, this is something we are trying to do together to try to explore this new world. The challenge is very specific in Parkinson's disease, in olfactory tract. But the idea is that we start by with unsupervised approaches. Labels are not so easy to do, so we try to do some ablation tests to test our different information we can get in order to extract some meaningful prototypes. Then we can do a small annotation job, which is taking a lot of time, taking expert time. Work in few shot supervised learning approach, for example. Then go and do XAI to understand what we are doing, try to associate, correlate find causalities, if any, and generate likelihood of the hypothesis we propose, or try to generate new hypotheses. I do like this kind of approach. Why? Because it's a Bayesian approach, in which I will start by the facts, and I will try to estimate the likelihood of an hypothesis, which is different of the frequentist approach, which is starting from the hypothesis and trying to see if the facts make sense. So both are complementary, but we don't need to forget Bayesian one. So I like very much this kind of approach, and we are trying to do it and to apply it in our system. So now I will try to be a bit more explainable and instantiate what I'm talking about, and try to present you some of the examples we had. So this was about phagocytosis activity analysis in frontotemporal dementia, ALS. We have some genetic mutations which are known, and the idea is we don't really know exactly the mechanism through which this kind of, let's say, genetic mutation is influencing things. And the study we did was just about one aspect of it, try to measure the aggressivity of the cells. So here you have an example of such a study, such a setup in which we have phase contrast in a dynamic environment, very difficult to handle from the computer science point of view, computer vision point of view. Why? Because we are in a 2D image, but with a lot of effects, halo effects, and making a proper segmentation and tracking on that, it's still challenging. So you have some systems able to do that. One of them, it's our system, which we published recently. And there is also some competitions, concurrent systems. So you can see here that it's not always easy because the adherence to the plateau is different according to the dynamic and to the moment of the evolution. And then the idea is to measure the dynamic of the cells. Here, the red part you see here, it's like a sort of aggregate. The cells will need to consume, and we measure the aggressivity of the system, of the cells, according to the speed of this kind of consumption. And from that we created, again, LSTM models. I will not go into the details of the model we use, but they are dedicated to temporal sequences, and they are specific also to some very difficult phase contrast images we are working on. And you can see here the colors. This is one of the method of the explanation I was talking about. It's a visual explanation about what we are doing, okay? So here you can see the cells activating. You can see the background activation. So why is this interesting? Because then you see how your system, how your model is doing the job. You can follow that, you can track that, you can be okay with it, or you can change everything if you don't agree. But at least the system is showing you how they did step by step activate a cell to make an interpretation of these cells, or how they get rid of the background using this kind of information. Another interesting takeaway message from this, and so by the way, this algorithm is published. It's you have a GitHub link, so you can try to use it on your own images if you have such a phase contrast videos. And the interesting takeaway message is also that here you have our system, which is represented with this kind of grid. And star beast, it's a concurrent, cell pose, it's a concurrent, and our system is here. And you can see that, for example, the execution time, it's really at the state of the art for us. You can see also that the precision is good compared to them, and especially you can see the number of parameters, which is much lower. And I was talking about green footprint. Our system has a much better green footprint than the others by still doing the same kind of performances. And here you have a comparison with the two major competitions, StarDist and CellPose. StarDist was published in Nature Methods, and our system is having overall a very good performance for the whole range of IOU. And also, as I was telling you, what is interesting is that you can earn explanation, you can have a good precision, and you can certainly divide by 10 or 20 the green footprint of your system and model. And for me, this is interesting. Why? Because most of the people are saying, yeah, if I'm trying to explain things, I will lose precision. It's not always the case. You can see this example, right? Precision is still at the state of the art here. You reach state of the art precision with these models, and you are dividing by 10 sometime the consumption of your models, the workload of your models, you need to pay to make this kind of things happen. So this is very interesting. We created also an automated deep learning optimization system in which you are able to use different execution time, GPU memory usage, and this is like related about to performance and precision to reach like the best configuration of your system. So this is an automatic way to somehow design your system. So again, because we try to be explainable, we optimize our system to do everything in a good compromise. Much faster, much less consumption, and reaching the same performances. Another example I would like to talk about is the stratification of Alzheimer's disease. So patients, by the analysis of whole side images and computational pathology. So what was the challenge here? We work on brain images, human brain images, very difficult to get, very difficult to work on. And we were focusing in this project on one particular problem, which is the tau proteins with different aspects. You can see here the tangles, the plaques, the neurites also are present. With different kind of biomarkers, we can see that in a very good way, I would say. The problem is, like always, the devil is in the details. Annotation. So here you have an example of a pipeline which we published in 22 in MICAI, using some simple explainable segmentation methods, especially based on attention, visual attention. Here you have the ground truth. Here you have the original image. We are talking about plaques, neuritic plaques here. So the annotation we had was this one and this one from the pathologist. So after different iteration, you can see here the system is showing us the hotspots in a more and more refined way. And we reached something which was probably like iteration 1000, this kind of scheme in which we can see like a pattern popping up here. And the problem we had with this system was that finally the pathologist was realizing that the errors he's making were probably about 20 to 30%. Okay, so we reached like 70 or 80% of accuracy. So he has 20% of errors. Who is the best? Can I base my score on his expertise? Is it right? Does it make sense? So we need to ask ourselves this question. And now we are in the process in which we are trying to put together the annotation of the pathologist with AI's work and try to find the best correspondence to try to see if we are able to refine this annotation, and the refinement is to be done in an environment in which we have a cloud-based platform in collaboration with Cytomine, which is a Belgian initiative starting from University of Liège, in order to put together the annotation of both pathologist and AI, and try to have a discussion about this, to consolidate the problems. Another effort we did related to the same project was to study the layers of the brain. So here we had like a very important effort of annotation with 6 layers, 3 layers, done by our pathologist. So we did study again this problem with attention maps to see the hotspots. And we created a set of graphs. So I will not go into details now, but we can discuss more about if you are interested. The graphs are like flexible. We can adjust, we can adapt. And then we did work on with classical machine learning and also with GNN, which is a graph neural network, working on this kind of support. The interesting point is that on these kind of graphs, we were creating a double information. One was topological and the other one was morphological at the nodes. So we used to say that it's a meta graph, maybe the word is not good, in which we are putting two elements, topology and morphology, to work. And then, of course, this can be analyzed using classical architecture. We choose 5 GNN architectures. We have a set of parameters which have been used. There is an explainer, 2 different types of explainer existing on GNN. And we did work this information to create clusters to understand if we do have a sort of correlation between the tau pathology distribution and morphology and the stratification of the patients. Again, sharp values are used to find the best parameters, and at the end of the day, we can have a sort of result in which we put together node and edge and try to make a correlation and give the importance of this element across the layers. So, talking about perspectives, I will finish by these kind of few slides. What we do in the future, of course, we talk about integrative computational pathology. This is like a Trojan horse, in which pathology, it's a very important point in the diagnostic process. So the only way to bring omics in clinical studies and in clinical routine will be to pass through the pathology. If the pathologists will not agree, nothing will happen. So this is like a Trojan horse for the omics, to try to bring the omics inside. And of course, people are talking a lot about spatial transcriptomics nowadays, which is exactly that. How to bring spatial information with omics through the diagnostic process. Another and the last, let's say, perspective I would like to talk about, it's representation learning. So you may have heard about this keyword. So data annotation, as you saw, it's a complex bottleneck, complex pattern. Do again, like the problem I was showing you on Alzheimer. We spend a lot of time on the annotations. So now the idea is to work on self-supervised learning approaches. Try to have this kind of like segment anything approach, which exists already. Meta created that, it's working quite well. To work on these images and also to have a self-supervised learning for representation models, foundation models like Dino. In the second version they have to work on what? On our images, which will be like MRI images in our case. So working together in a self-supervised learning process with representation learning, for me, it's very promising. We will be like putting together computational power with advanced expertise and massive MRI brain data set. And the idea is, without going into the details, to be able to go to a sort of brain MRI. I call it Oracle, just again to tease you, challenge you. But this is possible now. By aggregating massive data sets, we can do that. And I believe India has a very important role to play in these kind of challenges. Nobody did it yet on MRI, so let's play the game together. Okay? Thank you very much. This is my team.
Long live India and France friendship.